morning, everyone. I hope you're all as excited as I am for today. We're going to have a full-on day, full-on half day of a very enjoyable talks from a range of diverse researchers. And we'll be kicking off today with a talk by Debbie Zhao. Debbie obtained her PhD from the University of Auckland last year on the topic of creating personalized models of the heart from 3D echocardiography, during which she also trained as a research sonographer. She is a research fellow in the Heart Mechanics Research Group at the ABI and holds honorary research appointments at Bart's Heart Centre NHS and King's College in London. She was recently awarded a Putahi Manawa fellowship to carry out a large heart imaging study with the objective of redefining reference ranges for equitable heart health in Aotearoa, New Zealand. Please welcome Debbie.
Good morning and good evening for those joining from Boston, and hello, I guess, to everyone else from anywhere else. So for those of you that don't know me, my name is Debbie. I am a research fellow at the Cardiac Mechanics Group at the ABI, which comes as no surprise since I'm going to be talking about cardiac imaging. But first, I just wanted to thank Matt for putting me first, because usually the first talk means that there are no expectations yet. But anyway, so I actually, just one more piece of good news. Matt asked me, well, I asked Matt what I should talk about, and he sort of just said cardiac imaging in general. So I looked at, well, I thought about what I wanted to talk about today, and the good news is that the first talk of the day is actually not going to be too technical. Instead, I'm going to talk about something that I'm really passionate about, which is the translation, well, clinical translation of AI. And what I mean by clinical translation is basically taking our AI models and applying them to real clinical data. So this is clinical data that comes with all of its caveats, the inhomogeneities, vendor differences, and all of that. So, the heart is a very important organ, and a lot of us like to say that the heart is the most important organ in the body, and for anyone who disagrees, you can come and talk to me afterwards. The heart is actually a very complicated organ as well. So it beats about 100,000 times a day, which is about 2.5 billion times in your life. And it relies on a series of coordinated electromechanical events to make sure that each heartbeat is optimal, and to make sure that the heart is also able to adapt to the changes in oxygen demands of your body as you live your daily life. So in order to make sure the heart is functioning properly, cardiac imaging is extremely important. It shows us how the heart is in its structure, it shows us how the heart is functioning, and thanks to cardiac imaging, luckily, we know that the heart actually looks something more like this. So there are 4 chambers in the heart. There's a left side and a right side. So in order to pump blood around the body, the heart actually has to generate really high pressures. So you can think of this as squeezing a tennis ball, and the amount of pressure that's required, that's essentially the forces your heart has to generate and able to pump blood to your brain and your arms and legs, for instance. Which is why you can see here the left ventricle, which is the largest chamber of the 4 chambers. The walls are thick and muscular. Clinically, the left ventricle is also the one that we most commonly assess, because it is the chamber that acts as a systemic pump that has to withstand those high pressures. The other 3 chambers are actually also very important, but due to limitations in imaging and somewhat a lack of understanding, and in another sense, the left ventricle being sort of the symbolic chamber of the heart, we tend to put most of our focus on the left ventricle. So it's a good place to start. The good thing about cardiac imaging is that it lets us go from diagnosis, serial patient follow-up, deciding what treatment to do, and then observing whether the treatment have worked. The downside is that it actually creates a lot of work for the healthcare system. So as an example, these days, oncology treatments, cancer treatments, have found to have potential negative side effects on the heart, which means that patients undergoing cancer treatment for other parts of the body actually also get routine echo follow-up, and so on and so on. And essentially, we're taking these techniques in a way for granted because we want to continuously monitor the heart. And what happens is that there's this buildup of very high demand, which essentially most healthcare systems can't keep up with. I'm not sure what the situation in Boston is, but in Auckland, we've got wait lists of up to a year, so thousands of patients on the wait list. We can't see them, give them their diagnosis, which eventually leads to delayed treatment and poorer outcomes as well. So this is something that's really important and something that we need to do something about. So along with sort of the imaging side of things and making sure we can get the scans done and get the scans analyzed, there are also there's a continuous effort in terms of deriving new biomarkers. We're always looking for early detection and screening, but this I think of as a luxury. If we can get through our already pre-existing wait list, then maybe we can start focusing on early detection. But we know that early detection is important because we want to sort of go for the prevention model rather than catching people once they've fallen off the cliff already. And so with imaging and with analysis, there are actually two sort of quite different streams of how we look at these images. So from a research perspective, we're often looking at high fidelity geometries from the analyses, and we want to input these into more sophisticated pipelines such as biomechanics, maybe shape analysis, and then this gives us more detailed information for the characterization of cardiac health and disease, potentially. Clinically, they're typically actually only interested in very simplified measures, things like the volume of the heart at a given point in the cardiac cycle or along the heartbeat, and usually basic linear measurements such as wall thickness, or maybe a diameter or a length, and also combinations of these simple measurements for ratios and so on. And so just a brief, I guess, summary of the cardiac imaging workflow. We start with acquiring some cardiac images, and there are multiple modalities. There's MRI, CT, ultrasound, but also called echo. These images get analyzed either by software or a machine or a person, usually someone, hopefully, who's highly trained. From these analyses, then we can derive sort of some of the indices I was talking about before, whether these be your sort of 3D or 4D geometries or just your linear basic measurements. And hopefully, this can be used to inform sort of something about the patient's state of health, and hopefully tell the clinicians what sort of treatment the patient should undergo. So the two main modalities I will focus on in my talk today will be MRI and echo. So cardiac MRI or CMR, depending, is the gold standard for anatomical cardiac imaging and chamber quantification. For those of you that don't know, cardiac MRI uses magnets, hence the first part of the title of my talk. Essentially, it uses the hydrogen atoms in our body most commonly, and when placed inside a strong magnetic field, such as that of an MRI, all of these atoms actually align. What you can then do is apply radio frequency rays, which will then tilt the alignment to out of alignment, and then eventually these will go back. Once they go back into alignment, this releases energy. So depending on the, I guess, composition of your soft tissues and how much hydrogen atoms there are, we can use these differences in energy to generate an image. And so cardiac MRI and MRI in general is really good for soft tissue imaging. So if you want to look at different parts of the tissue, if you want to look at scar or different compositions of soft tissue, then MRI is sort of the modality to go for. The resolution is about in the millimeter range for cardiac. So cardiac is a special type because the heart is something that moves. So the sequences are also optimized for temporal resolution as well as for spatial resolution. So if you are imaging other parts of the body, you typically could get higher resolutions. But nevertheless, for MRI, it is still the gold standard in terms of structure and function, which basically just means geometry and volumes. Echo, on the other hand, is another non-invasive imaging technique, but it is poor resolution. There's shadowing, there's a lot of artifacts, speckle noise, and the images are also not, the resolution, if you like, is anisotropic. So it's more difficult to deal with MRI typically. Logistically, as you can see in my beautiful diagrams, Echo is usually better tolerated by the patient. So there are a number of contraindications for MRI. So for example, claustrophobia, people with pacemakers have to undergo additional sort of checks. It's non-portable, it's only accessible in large centers, and it's very expensive. So each cardiac MRI that we perform at the Center for Advanced MRI across the road from Auckland Hospital, for example, is about $2,400. An ultrasound, an MRI takes about 1 hour to do your full cardiac scan, and ultrasound about the same. So the cost is significantly lower. So it's about $500, I believe, which is still relatively expensive. But compared to the MRI, there are a lot more echo machines. It's portable. You don't have to visit a large site, and we can take these out into the rural communities as well. So the important part of echo is a wider clinical reach. So actually I forgot to mention, so echo is an ultrasound technique. So this essentially uses sound waves which are able to pass through the body. When they hit two surfaces which have different acoustic impedances, this generates an echo, and hence the name echo. So if something is further away from the transducer, then it will take longer to echo. So we can encode that information as a distance. And then the brightness or the magnitude depends on the difference in your boundaries or how reflective specific structures are. So if we think about the heart again, and all its four chambers, we can think about how the imaging sort of works between these two modalities typically. So MRI is usually an exam that consists of multiple slices across the heart. So essentially you're able to create a 3D representation from multiplanar 2D slices. And because the patient doesn't move inside the magnet, you know where the slices are relative to every single other slice. And this is very useful because we can then put all these slices together, which I'll show in a couple of slides later, to generate sort of the full geometry. 3D echo, on the other hand, is just sort of a single snapshot modality that is able to capture the entire 3D image. So there's no sort of 2D planes. 2D echo is much more widely used, but if you think of 2D echo, you don't actually have a reference. You're able to take independent 2D slices, but you don't know where they are relative to each other because there is no magnet to act as your coordinate system. So this is just something to remember. And then here are examples of the images. On the left-hand side, you see the MRI. So there's 3 slices here. It's a bit hard to see, and a short axis slice. And like I mentioned before, because you know where they are relative to each other, you can sort of reconstruct this image of the heart. On the right is a 3D ultrasound. This structure here is the left ventricle. So it's a focused 3D echo. And even then, you can tell that if you were to manually segment this image, it would be very difficult because there's no clear boundaries. MRI, it seems like you could almost just use a thresholding approach, and that would give you a myocardium, but 3D echo is a much more challenging problem. So the 3D echo image is acquired in 1 breath hold and 1 heartbeat. Essentially, that's your cardiac cycle. The MRI typically has about 6 to 8 short axis slices and 3 to 4 long axis slices. Each one of those is about a 10-second breath hold, so it's significantly longer. So when it comes to medical imaging these days, the first question when you want to segment an image is why not just throw it at a neural network? Turns out you need training data. So while this is great for MRI, we've got the UK Biobank and experts who have manually sort of segmented multiple images, 3D echo is much more difficult to segment. So existing data sets, even if people were to acquire them, have taken hours for expert cardiologists to segment them. Unfortunately, what they found was that the inter-observer variability between experts was really, really large. And so if you have this amount of variability going into the machine learning, there's not much you can expect it to do in order to correct for that variability. So instead, we had this other idea, which was essentially to leverage the higher resolution of MRI or CMR and use this information to create sort of reference labels to train a machine learning network to analyze a 3D echo. So these were the two objectives. One, make some labels. Two, train a network. Sounds simple enough. So here's a sort of visual representation of what it would look like. So this would be cardiac MRI images and a 3D echo from the same person's heart. And over here, we're focusing on the left ventricle. That's our sort of structure of interest. And ideally, we want to be able to extract that white wireframe mesh on the left ventricle directly from the 3D echo. And so we built up this data set called Matia based on images we acquired here in Auckland. So I think I updated the numbers slightly. We recruited about 167 patients, of which 154 were included. Some were excluded due to poor image quality or failed MRIs or abandoned scans and so on. And essentially, we can analyze the MRI of these patients in a different sort of, so it sort of looks like this. This is a cardiac MRI of the one heartbeat. And then there are two sort of frames of interest. One is called end diastole. This is when the heart is at its largest. And one is called end systole, which is when the heart is at its smallest. So clinically, even though you do get this lovely sort of volume time curve, realistically, they actually only look at the 2 time points, which is what sort of we did here. So ED for end diastole and end systole. We extracted the geometries from the MRI at these time frames and then essentially registered them with the 3D echo in a process that looks like this. So the 3D echo is something that's 3D, so for visualization purposes, we can slice it however we want. And so I basically did this for all of the ED and ES frames for all of the patients. We also, to assess scan, rescan, repeatability, we actually did 2 3D echo scans for each patient. So that results in sort of 608, 154 times 2 frames times 2 scans, so that's about 608. So basically I repeated this process 608 times. And this is just a rigid transformation, essentially an alignment process based on some an initial estimate that we know using landmarks. So I guess it wouldn't be an AI talk without one of these diagrams. Long story short, we just took NNUNet, which is a very well-known off-the-shelf sort of unit model, and just applied it to the network. Applied it to the data that I just described. A lot of numbers here. These are from my paper, which I forgot to mention. You can sort of look up. But essentially what we found was that there was an increase in accuracy compared to the current sort of status quo, which is an expert manually analyzing the 3D echo images. Essentially, if you look at the bias column of the NNUNet versus the bias of the expert manual, the biases are typically actually less than half, and if not much less than half in systolic volume. We see an increase in intra-class correlation coefficient, and also in terms of repeatability. So when we got the manual expert to manually analyze the 2 images that belong to the same patient, their discrepancy was much larger than the NNUNet. So the outcome, I guess, of the study was that we were able to generate this 3D echo and MRI data set, which we publicly released. So the component we publicly released was the 3D echo images plus the MRI labels that were registered. And essentially it's an application process. And then on the right here, it's just a visualization of the tables that we showed before. What you want to notice is that these blue bands, which are what we call the bias, so the difference between echo and MRI, with the NNUNet, they're sort of much thinner, and same with the limits of agreement. So that's a measure of the variability. So if you want to access the data, you can actually fill in a short Google form, which I will then read and approve, hopefully. We have had about 40 applications as of this year. This was released earlier this year with all sorts of people doing all sorts of very interesting things. So I always enjoy reading the applications. So given that we can have LV segmentations from 3D echo, sorry, LV being left ventricle, what next? Well, one of the obvious things is to extend it to the other parts of the heart. If you recall, the heart has 4 chambers and we looked at 1. So there's someone, Joshua Dillon, who is also from our group working on RV segmentation, essentially building on the methods that I described, applying this to the RV, and hopefully in the future we'll be able to do both ventricles at the same time, which will be very exciting. We can also, I guess, use these measurements and take them further into in a clinical context. For example, one of the applications is LV remodeling. So this is seeing how the left ventricle has changed, basically using the ratios that I talked about. So wall thickness versus diameter, or wall thickness versus volume. They're sort of different categories that the patient can be placed in, and depending on which category, their treatment plan actually changes. So MRI, if you recall, is the gold standard for classification. And what we find clinically is a lot of patients go to get 2D echo, they get a classification, and then the clinician doesn't quite trust this, and most of the time they'll get an MRI. What we do find is that 2D echo tends to estimate disease. And so a lot of the MRIs we get are actually turn out to be normal, which is not good given that it's a scarce and very expensive resource. Using the same machine learning model, we were able to extract these wall thickness measurements and diameters and recompute these classifications. And we found that while 2D echo only had a 42% agreement with MRI, 3D echo had an 81% agreement. So it's still not perfect, it's not 100%, but it's much more efficient than what is done clinically today. With the 3D echo sort of ability to be able to analyze 3D echo, we've also looked at a number of different sort of heart-related diseases. So for example, we looked at atrial fibrillation patients. For those of you who don't know, basically it's where they have irregular heartbeats. This makes assessment very difficult, as I mentioned, because clinicians typically only look at one cardiac cycle and they only look at the sort of largest volume, the shortest volume. If you have got an irregular heartbeat, these volumes actually fluctuate. So we used 3D echo to see whether there was a difference between long beats and short beats, and what the clinical implications were. Another example is generating essentially pressure strain loops in hypertensive patients. And then with this work, we were able to assess whether the analysis of pressure strain loops in different groups of hypertension varied depending on medication status and whether or not they had hypertension. And another similar study looking at heart transplant patients and generating pressure volume loops. So with the 3D echo, the nice thing is we can combine this with other parts of clinical information, so such as pressures. And this gives us further insight in all sorts of different diseases, which hopefully in the future can inform new treatments as well. I guess just an advertisement for my colleague Edward, who is also using the Mattia dataset for something very interesting and I guess very trendy right now, and that's using diffusion models for synthetic data generation. It's good that we've got data from 134 patients, but ideally for deep learning applications, we typically like a lot more, ideally thousands and tens of thousands if possible. To manually collect this data would be not feasible and very expensive. So Edward's talk will sort of go over the use of diffusion based on this initial data set to see if we can generate new information. And so I guess this is sort of just a snapshot of what we can do. This is, I guess, more clinically oriented. It was a diagram I drew for our clinicians. Given that we've got magnets and sound waves and AI, we're able to build these 3D models and then extract whatever they want from them. So it's really nice, I guess, that we get to work very closely with our clinical collaborators, and they essentially inform us what the green boxes are that they want, and we try to compute that for them. So in summary, a fundamental paradigm shift is actually needed to address sort of the shortage in resources. And this is not just speeding up one component. We really need to think about, can we use new technology and new AI and new ways of thinking to be able to get measurements that we typically need in clinic. The quality of training data is important for AI applications, and consider using new ways other than the norm to generate your labels. AI has the potential to automate and accelerate cardiac imaging workflows, which can go all the way from image acquisition to diagnosis. And at least in my head, the future of cardiac imaging is accurate, accessible imaging all in the time span of a single heartbeat. So I'll just quickly thank some people. As I mentioned, this is all sort of translational work, and we would not be able to do it without our clinicians, our research, our cardiac sonographers, our MR technologists, all of the other people in my lab group who helped me out, and of course the patients that we've recruited for the study who have volunteered their time and given us their data. And thank you all for listening.
Just taking any questions now from the audience, either here or over in the US through Zoom.
A question regarding your observation on when you use the ultrasound images tend to overestimate disease. Do you reckon it's because of a feature of the image, or is the clinician trying to be erring on the side of being careful?
It's definitely a feature of the image
Okay.
in this case. So in the example that I gave to do with, I guess, remodeling, it's a very easy to explain phenomenon if you look at the images side by side. Because of the poor resolution of the 3D echo, what happens is you tend to overestimate the wall thickness. So increased wall thickness in a cardiac sense means hypertrophy, typically means your heart is working too hard and so the muscle has thickened. So essentially because of the lower resolution of the echo, and sonographers, well, cardiac sonographers typically are the ones in New Zealand anyway that write the report and make the measurements. They don't actually get exposed to MRI very often. So measurements that come from sonographers just purely by visually looking at the image and trying to measure a wall thickness, it tends to be overestimated.
Okay.
Yes.
Great talk. So your 3D echo, it's really 4D, isn't it? Because you've got a temporal component, but you're throwing a lot of information away, just extracting 2 time points.
That's right.
What ideas have you got for making better use of all of that information that you're already gathering?
Yeah, so at the time I did my PhD, we didn't have the big GPUs in our HPC that we do now. So anyone who works with 3D data will know that if you're running machine learning models, memory is a big issue. And so one of the, ideally when we train, well, the segmentations models currently, we just input one single frame and one label, and then we're able to still I guess, create segmentations on every single frame independently, which actually surprisingly is not too bad. So if we look at the volume time frames, even without that temporal link of the time, they are still smooth and continuous for most of the time. There are ways in an AI sense to incorporate this temporal information using things like transformers or LSTMs, for example, but they do sort of rely on memory, which actually isn't a problem anymore because of the better GPUs, but also if you could consider adding dimension reduction techniques to reduce the amount of data, which in the end is actually not very much. So if you think about 3D echo, it's an interpolated sort of everything up here. There's a lot of interpolation because the beam lines are further apart. So you definitely making use of network architectures that account for temporal information, I think would be very useful. But for now, at least for the analyses that we're doing, it doesn't even seem to be necessary. The network does a pretty good job at just segmenting the left ventricle independently.
Thanks, Debbie. So I was interested, you said, so you do the MRI and then you do at least one echo, but maybe multiple. Is part of that, so are those multiple ones, multiple operators? Do they tend to be the same operator, multiple machines?
So ideally, we could get multiple operators and multiple machines, but it's a logistical limitation. So all of our rescans for 3D echo are the same operator and the same machine.
So just as a follow-up question, I mean, how different are the outcomes between operators?
Between sonographers?
Yeah, for example, yeah,
Yeah.
or even machines for that matter. I'm operators in inverted commas.
Yeah, so one of the actually very interesting things that some of our Part 4 students found this year, they were tasked with looking at the effect of image quality relative to model performance. So we know that image quality in echo it's also very complicated, but there are ways of subjectively scoring them. And we know that image quality is very operator dependent. So it depends on the expertise of the sonographer. If they're experienced, they tend to get better images. If not, they haven't optimized the gain and the contrast and so on, they're poorer. What we found with the machine learning is that actually image quality does not impact the performance of the machine learning model anyway, which is good, but image quality does impact the accuracy of manual segmentations. So we did, in our, I guess, study, we didn't have the scope to switch operator. We're lucky enough to have one sonographer. So yeah, that's something outside the scope, but at least it seems to be promising that at least it's not operator dependent.
We have time for one more question. Yeah.
Yeah, you mentioned that the ultrasound is basically a radial coordinate system.
Yes,
and
that's right.
Standard NN unit is Cartesian.
Mm.
Do you convert it to Cartesian before?
Yes,
into the-
that's right. So essentially, this is the image that goes into NN unit. It's already been, I guess, resampled at Cartesian locations, but the raw Cartesian data, if you like, is in polar coordinates.
Thank you.